Good morning, champs! In the previous video, we introduced the basic building blocks of potential flow. Now, we take the next step and look at flows that already resemble real physical situations. We start with the dipole. You can think of a dipole as a source and a sink of equal strength placed very close together. No fluid is added overall, but fluid is pushed in one direction and pulled in another. Instead of starting with that construction, we begin directly with the velocity field. In cylindrical coordinates, the radial velocity is minus m over 2 pi times cosine theta divided by r squared. The tangential velocity is minus m over 2 pi times sine theta divided by r squared. Both components decay with 1 over r squared. That means the dipole becomes very weak far away from the origin. So it is a very localized flow. Now we determine the velocity potential. The radial velocity equals the derivative of phi with respect to r. So we integrate minus m over 2 pi times cosine theta over r squared. This gives phi equals m over 2 pi times cosine theta divided by r. Next, we determine the stream function. Using the relation for the tangential velocity, we integrate and obtain psi equals minus m over 2 pi times sine theta divided by r. Now, we combine both into the complex potential. The complex potential is phi plus I psi. This gives m over 2 pi times 1 over z. So the dipole has the compact form f of z equals m over 2 pi z. Physically, this flow is directional. Fluid approaches from one side and leaves on the other. This is why the dipole is so useful. When we later combine it with a uniform flow, we can model flow around bodies like cylinders. Next, we consider stagnation point flow. A stagnation point is a point where the velocity becomes zero. The velocity field is u equals ax and v equals minus ay. So, the velocity increases linearly as we move away from the origin. From this, the potential becomes 1/2 a times x squared minus y squared. The stream function becomes a times x times y, and the complex potential is 1/2 a times z squared. This flow represents fluid approaching a point and then splitting into two directions. You will see this pattern at the front of objects in a flow. Finally, we introduce the most important idea in potential flow: superposition. Because Laplace's equation is linear, we can add solutions together. For example, we can combine a uniform flow and a source. The complex potential becomes uz plus e over 2 pi log of z. This combined flow produces a shape called a Rankine half-body. And this is where things get interesting. In the next video, we will analyze this combined flow step by step and use it to determine the contour of a body.